Okay, let's get the show on the road. So, you can get your QR code right away. And anyone else coming just a minute late, sorry about that, but you know, they're online. Are we good? Okay. Quick review. So, we're continuing on differential equation, but we're looking at a totally different method of computing solutions other than using the matrix exponential for linear systems. This is called the Laplace transform. It takes a function in what we call the time domain, things that depend upon time, and transforms it into a function that is often called the frequency domain or the Laplace domain. How it does it is with the improper integral 0 minus to infinity f of t e to the minus st dt. That integral will converge for some values of s, but usually not all values of s. And the values for which the integral is well defined is called its region of convergence. An important fact, if you have a function that is differentiable, and it has a Laplace transform, then it is related to the Laplace transform of f by s, capital F of s, minus f at 0 minus. That 0 minus we will start using today. It's important for solving ODEs. And so mostly engineers, we don't go around computing that integral. We instead use a table which has time domain functions on the left, to the right of that, the Laplace transform, and then mostly we ignore the region of convergence. Yes, it's great that somebody computed those, but for the single-sided Laplace transform, which is the version that we are doing, it's not important. And then there's this list of how the Laplace transforms of various derivatives of a function can be related back to the Laplace transform of the original function. And we'll be using those when we solve differential equations today. And so we've done one little simple example, but that's all. Okay, so we're going to start today on computing inverse Laplace transforms. I'm going to grab your QR code. Key method is called partial fraction expansions. I'll leave it as singular expansion. Okay, so let's just get into it. Start out with something that is a Laplace transform of a function, and we want to figure out what is the corresponding time domain function. We'll use really complicated numbers. Okay, so what we're trying to find is L inverse of f of s equals f of t. That's the goal. In a method of partial fraction expansion, I already have it written in terms of the roots. So just as we did when we were doing antiderivatives of rational functions. Okay, so we assume we can write it as a sum of first-order terms. Now I'm going to show you an easier way to determine those coefficients other than how we did it when we were doing partial fraction expansions for antiderivatives. There, we took and recombined everything and put them over a common denominator and got a numerator that involved K1 and K2 and then equated things to the original numerator. This time we're going to do something a little bit different. So I'm going to take f of s and I multiply it by s plus 3. Look what happens. K1, and I'll put the s plus 3 here, even though we know it cancels, plus K2, then I'll have s plus 3 over s plus 4. Now, because s plus 3 is one of the roots, that's why we have it on the right-hand side as one of the roots. Look what happens when I write s plus 3 up here. I get a cancel and a cancel. So let's just show that. So that equals, what did I have? S plus 2. Okay, so look what happens if I evaluate everything at s equals minus 3. So this part doesn't depend upon s. If I evaluated s equals minus 3, that part drops out. Here, those part drops out, and I just have to evaluate this limit. So I get this really important formula. K1 is f of s, whoops, sorry, I put that delta in. Okay, so here, I mean, I do need to do the limit, but the limit is easy to evaluate because it's deliberately set up so that there's terms that cancel. So that limit is now simply s plus 2 over s plus 4 evaluated at s equals minus 3. Plug in s equals minus 3, you get minus 1 in the numerator, you get plus 1 in the denominator, so that's minus 1. And the exact same reasoning works for K2. The limit s approaches minus 4, the root of the s plus 4 term, finally simplify, okay, so we get s plus 4, s plus 2, s plus 3, s plus 4, cancel, cancel. So that just equals s plus 2, s plus 3 evaluated at s equals minus 4. So what, we get 2 in the numerator, we get 1 in the denominator, so that equals 2. Okay, so let's just go back over this really quick. We're trying to find out what is the corresponding time domain functions. Things like this do not appear in our table. The things that look like 1 over s plus a, that's fine, no problem. So if we can write this as a sum of first order terms, that's great. The issue is all of the algebra it takes to calculate those coefficients. An easier way to do it than we did it for partial fraction expansion when we were looking at rational integrating antiderivatives of rational functions is to isolate each term, and you can isolate them if you multiply either one of these by s plus 4 through, it'll cancel, and then when you evaluate at the root, the other one disappears. Okay, so that's called the limit method. So we end up with f of s is minus 1 over s plus 3 plus 2 over s plus 4. And from our Laplace transform table, 1 over s plus a corresponds to e to the minus 8t times the unit step of t. So when you play with these for a little bit, you start memorizing them, just like d by dx of x third is 3 times m squared. Okay, you haven't played with them enough to have them memorized. But it's that easy to get the time domain functions. Minus 1 e to the minus 3t times unit step of t plus 2 e to the minus 4t minus 4t unit step of t. Okay, so we try to rewrite the function in a form where we can use our table. That's how we do the inverse Laplace transform. Okay. So our table has simple Laplace transforms in it, but doesn't have products of roots and things like that. So that's how partial fraction expansion fills everything in. Do you want to do it the old-fashioned way just to see the comparison, or is this clear enough for you? What do you prefer?
Comparison?
Comparison?
No, this is good.
Yeah. Okay, so let's just do it really quickly. Whoops. Need a color. S plus 2, S plus 3 times S plus 4 plus K1 over S plus 3 plus K2 over S plus 4. And so we separated it, and then we immediately recombined everything. So this would be K1 times S plus 4 plus K2 times S plus 3. And then we equate numerators. So what do we end up with? What's multiplying S? Okay. So we end up with S plus 2 equals S times K1 plus K2 plus 4K1 plus 3K2. The only way that can work for all S is if K1 plus K2 equals 1, then 4K1 plus 3K2 equals 2. And then you solve simultaneous equations. So when it's 2 roots, it doesn't really matter. Already at 3 roots, this is so much easier. Okay? It isolates each and every term where you're just plugging in values. Okay? And especially if you use Julia for doing the plugging it in. So here's kind of the general result. F of S, some crazy numerator, or some crazy denominator, where these have real coefficients. So they're standard polynomials, the numerator and denominator. Assume that the degree of n of S is strictly less than the degree of d of S. 1 less, 2 less, doesn't matter. R1, R2, Rn. The roots of the denominator polynomial. And you can write f of s k1 over s minus r1, k2 over s minus r2. Whoops, these are roots. And they should be distinct. Plus dot 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 Kn over S minus Rn. Ki equals the limit as S approaches Ri, S minus Ri, f of S. You can always do it that way. Because S minus Ri is a root of the denominator, it will always cancel. And this limit can be evaluated just by once you've done the canceling, then it's n of s over what's left of d of s. Okay? So this will be n of s. Let me write this differently. It'd be more tolerable. Right, it's s minus ri dot 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 s minus rn. Put the s minus ri here. So that those cancel, then we simply evaluate everything with s minus ri. And it's the same method as before. By multiplying by s minus r2, we would isolate k2, and then the s minus r2, when we evaluate that at s equals r2, that would go away, etc., and we isolate k2. And the same thing works for 3, 4, 5 up to n. So that's the general formula for getting the partial fraction expansions. And you'll do 3 or 4 of those by hand in your engineering courses. Okay? And you'll use software when you do that. In real life, on the final exam, etc. So we're not going to do it by hand on the final exam. Okay, so that's how you find, once you've got the partial fraction expansion, then you use the fact that 1 over s minus ri corresponds to e to the rit unit step of t. You do inverse Laplace transform of each term. If there's a minus sign here, there's a plus sign here. If you put a plus sign here, you put a minus sign there. So you just have to go back to the tables, get used to it a little bit. Okay. So f of t, which is the sum, I equals 1 to n of the e to the rit unit step of t will always be real. Good. Real, I don't see anything complex. Well, no, you do, because you know roots of polynomials can be real and they can be complex. Even a quadratic can have complex roots. Okay. So Euler's formula is going to show up here, and we'll talk about that in just a second. But the imaginary parts have to cancel because if the function, the original function was real value, then when we do f of s and the inverse Laplace transform, it's going to be real as well. Okay, questions on this? Kind of see where it comes from, but doing it is just, well, you don't need, I like to say, it's just algebra. We go about just the stuff that we're not very good at. Yeah, so it's just algebra. The nice thing is you don't have to do a fancy integral in order to compute the inverse Laplace transform. There is one, but we don't need to do it. So to compute the Laplace transform in theory, we need to do an integral, but in fact, every function that an engineer will ever face has already been tabulated, so doing the integrals is kind of pointless. And then the hard part is finding the inverse Laplace transform once you've done the Laplace transform, and that's where the partial fraction expansion is. Okay, so we're not handling repeated roots, so let me go back and just show that repeated roots happen. Things that have a t in front, notice that has a root at s equals 0, n plus 1 times. T in front, repeated real root. T in front, there are repeated complex roots here. The t in front, repeated complex roots. So that case needs to be treated separately, but it doesn't come up very much, and so we're just not going to spend much time, not going to spend any time on it. Okay. So if the denominator has distinct roots, we factor it, we do the partial fraction expansion, we compute the terms, try not to make too many errors, do inverse Laplace transforms, and then we have to add up all of the time domain functions. It's getting to be a lot, okay? It's getting to be a lot. So facts, if Ri is a real root, the coefficient Ki is real. Yeah. Not hard to show, you just gotta use facts about multiplying roots. That if you have a real polynomial, the roots occur in complex conjugate pairs. That's a fundamental theorem of algebra. Now, so this is actually it's if and only if, so I'll add that there. So if the root is complex, then they do occur in complex conjugate pairs. So let's suppose Ri plus 1 is the complex conjugate of Ri. And the coefficients Ki occur in complex conjugate pairs. Remember, it's when you take the imaginary part and put a minus sign in front of it. So as an example, let's do one real root, complex root, and then it has to have its complex conjugate minus it. So it's third order denominator. The roots occur in complex conjugate pairs, so everything is real when you multiply it out. We don't care what the numerator, as long as its degree is 2, 1, or 0. Okay, so in this case, the roots are minus 1, minus 2, minus 3i, minus 2, plus 3i. Those are the roots. This one is the complex conjugate of R2. You know, if you write down the other one first, then the last one's going to be the complex conjugate. It doesn't matter. Okay, so that's just properties of polynomials. Then the coefficients become, I've already computed them for us. K1 is 3/10, so R1 is real, K1 is real. R2 is going to be complex because, K2 is going to be complex because R2 is complex. And that's equal to minus 3 over 20 minus I over 20. And the point is, you don't need to compute K3 because you know it's going to be the complex conjugate. We'll write it out. So they appear in complex conjugate pairs. The coefficients and the roots. Okay, so that's just facts about polynomials. Questions so far? How are we doing online? Tape, everything good? Okay. So, what we've done so far is taking functions, produce Laplace transforms, give it a Laplace transform, produce the time domain function, and now let's show how in general we solve differential equations. Okay, so this is the red flag order. Okay, so we give us a differential equation. So we're going to take y triple dot. Oh no, I wasn't that brave. Y double dot. Y triple dot's the next one. Y double dot. 5y dot plus 6y equals u plus 7 u dot. So u is the input. So it's like a torque on our joints, etc. U, I have the numbers worked out. I'm going to use another simple function, e to the minus t, s of t. We're going to have non-zero initial conditions. So y at 0 minus is 2, y dot at 0 minus is 3. This is the so whenever you have derivatives of the inputs, if that was a third derivative or fourth derivative, it doesn't matter. U dot at 0 minus is 0. U double dot at 0 minus is 0, etc. So that's the warning, and that's because U of t is assumed to be right-sided. Okay, so that's where in the beginning all of us make make the mistake. We know that the formula here, when we do the Laplace transform, is going to be s y of s minus y of 0 minus, and we want to do the same formula here. But u at 0 minus is always 0. Even if the function is cosine of t, which at 0 is 1, at 0 minus from the left, it's 0. Okay. That's where everybody messes up. So, stars, red flags, whatever you need. Okay. So let's just put in and solve it, and then I'll paste in a text summary that justifies some of the stuff. Okay, so we have our differential equation. It has a y in it. That Laplace transform is y of s. The Laplace transform y dot t is s y of s minus y 0 minus. And even though we have numbers, I'm not going to plug them in right away. You'll see why in a little bit. But then we've got a second derivative. The formula is, it's s times the Laplace transform of y dot, so that gives us s squared y of s minus s y of 0 minus, and then minus y dot at 0 minus. S Laplace transform y dot minus that's what that is. Separate. Once again, the reason I mention that is, even for me, when you get up to the third or fourth derivative, I thought, oh my God, is this s cubed times y of y triple dot 0? What is it? You know, no. You just start here and you write them down, and then the pattern is s times this minus y at 0 minus. Then s times this minus y dot at 0 minus. And if there's a third one, s times all of this minus y double dot at 0 minus, etc. So that's the pattern. S times the previous one minus the initial condition. Okay. Then in red, the dangerous stuff. Always 0, even if the function is e to the t, which at 0 is 1, but it's multiplied by the unit step, which is 0 for all t less than 0. So the limit from the left is 0. Okay, so we plug these into the differential equation. And you don't have it in front of you, so I'll help us get it written down. It's y double dot, so that's the s squared y of s minus s y at 0 minus y dot 0 minus. That's the y double dot term. Plus 5 times the Laplace transform of y dot. So terms get shorter. S times y of s minus y at 0 minus. So we just take the differential equation and we do the Laplace transform term by term. Then it had 6. So this one is easy. That's the y of t. Whoops. Oh. If I do t at 1, I might as well put t on all of them. We don't really need the t's. Then equals u of s plus 7s times u of s. So this is the u of t, and this is the u dot of t. Okay, so we just take the differential equation, y double dot plus 5y dot plus 6y equals u plus 7u dot, and we do the Laplace transform term by term. Okay, so we did them all separately and then plugged them in, but normally you wouldn't do that. You just take the ODE and you just start writing it down. Okay, so now we need to group terms. Okay. And I'm going to move the initial conditions to the right as well. Okay, we're going to do this in code in a little bit, but we've got an s squared times y of s, we've got 5s, we've got 6. Okay, so we end up with s squared plus 5s plus 6 times y of s equals okay, we got the u's right in front of us, so that one is pretty easy. 1 plus 7s times u of s. And if you want to write the 7s first, more power to you. That's what I had done in my notes over here. And then we've got terms involving the initial conditions of y. So this turns out to be s plus 5 times y at 0 minus plus y dot at 0 minus. And then you divide both sides by the s squared, and you've got y as a function of s. So y of s equals okay, I'm going to put the 7s in the front. Okay. then we've got these terms involving the initial conditions. Oh, let's just put them down as well. X plus 5, y 0 minus plus y dot 0 minus. Okay. Now there's a reason that I didn't plug in the input and the initial conditions. I wanted those to stay separate because this is general. We just did a second order. This is called the forced response. It depends only on the input. We don't care what the initial conditions were. They're all over here on this other side, forced response. Independent of initial conditions. So this is where the input is driving the system. So that's the part of the output that changes when you change the input. This is the initial condition response. Whatever initial conditions were set on the system, that part of the response is there no matter what input you apply. So it's independent of the input. And the fact that the output so the total response being the sum of the forced response nice. Sum of the forced response and the initial condition response that has a name. It's called the superposition principle. If you want to make a little joke to help you remember in a mnemonic, call it the superstition principle, okay? People will laugh at you, but they'll know you're talking about the superposition principle, okay? So, every linear system has this property that you can break up the response into a part that depends only on the input and one that depends only on the output. What this means is that you could solve this part separately from this part, meaning you set all initial conditions equal to 0 and excite the system. You could do that as a measurement, for example. And then you could set the input to 0 and vary the initial conditions and measure that part of the output. You add them together and you've got the overall response. Okay, so it allows you to divide and conquer. Okay, so. Okay, so now that we have this, what should we do? We should put in the Laplace transform of our input. I think that was e to the minus t, so that times the unit step. That's going to be 1 over s plus 1. And then we should plug in these values, 2 and 3. We should do the partial fraction expansions. Do the inverse Laplace transform term by term. Okay? And then we have the time domain function. Sound fun? Okay, so I'll let that soak in for a second. We'll take our break. It's 5:21.
It could be something.
I mean, it's all straightforward. If you consider computing roots of polynomials straightforward, you know. And it's all straightforward if you're okay dealing with complex numbers. It's all straightforward if you like algebra and don't make many mistakes. Okay, so we're going to do this in code. Let me do one other thing before I forget. So we're going to do 2 QR codes today. It's the day after April Fool's, okay? So we have to do something wild, right? So Devin, since you're here, you'll have to just very quickly at the end ask me to put that one back up so you can get it, okay? So if you remind me, it'll happen. If you don't remind me, it ain't happening. Okay, you got that? Okay. Everybody got it? Kane, we've got a second QR code. Today's bonus QR codes. Now, for those of you watching the lecture asynchronously, you can paste in the same 20 to 30 word summary for each of them, okay? But if you don't paste in anything, then it's double no points, okay? It's double zeros. Double bagel. We're good? We got this? Okay. So let's go to the code. Is that solar? Yeah. Okay. They all ran. Yay. Come on. Wish there was a top button. This thing on the side is too small. For my fingers, maybe this will get it. There we go. Okay. Closed form solution of an ODE via Laplace transform. So that's the same ODE that we just did. This is the grungy algebra that's in the book, where we jump to this last part. So the Laplace transform of this differential equation is this rational function times the Laplace transform of the input plus a second rational function that depends only on the initial conditions. So that's the superposition principle, superstition principle. And this has everything in, but let's do it in code. So we're going to use SymPy. We don't really need We're not using LaTeX-ify unless you turn that part on. So we're going to define a symbolic variable s. That's the Laplace variable. SymPy doesn't care if it's real, complex. It's just an abstract variable. I'm using my table to put in the Laplace transform of the input. So the input was e to the minus t times the unit step. Its Laplace transform is 1 over s plus 1. That's pretty easy to do. Just write that in. And then I said y0 is 2 and dy0 is 3. Okay, so that's the initial condition for y and the initial condition for y dot. The way the differential equation works is d of s, which is this s squared plus 5s plus 2 times y of s, okay? So here's what we had before. We had 1 plus 7s times the Laplace transform of the input plus s plus 5 times the initial condition of y plus y dot at 0 minus. The denominator term we divided by was s squared plus 5s plus 6. And so line 23 has the Laplace transform of y. Okay, so it's if you were doing it, I mean, you could plug in directly these terms here, and then there's actually tools in SymPy where you can just solve this equation written down in this first line for y. I'm simplifying it, so I'm not using those equation solving tools in SymPy. Okay, so I just wrote out in code the same thing that we had written out by hand. And then we got to this point that, oh my gosh, we have to do the inverse Laplace transform of 1 plus 7s times 1 over s plus 1 divided by s squared plus 5s plus 6, and then the inverse Laplace transform of that other term. And just went like, I'm not up for it today, okay? And you'll do that a lot yourself. And since this would take by hand 20 to 25 minutes on an exam, it's not very often that they want you to spend 25 minutes doing just algebra. And, okay. So we're going to get y. SymPy, expand and simplify, we'll just get rid of some of the common terms and things. Now here's how you do the partial fraction expansion, line 33. It's a part. It takes y apart into a bunch of terms. So that's the key thing, a part. So we'll print it, we'll print that out. So here's the Laplace transform with all of the numbers put in. 2s squared plus 22s plus 14 divided by s cubed plus 6x squared plus 11s plus 6. So if you wanted to do the partial fraction expansion of that, you need to find the roots of s cubed plus 6s squared plus 11s plus 6. Making me nervous just to say it because I don't want to compute those roots. So I'm letting SymPy do it for me. And it's done it. So the roots are s plus 1. Now notice how it wrote this root not in a form that we would like. We would like this as s plus 2. So multiply top and bottom by 2, and you'd have 22 over s plus 2. Why do we like s plus 2? Because that's how our Laplace transform table is written. We know that s plus 2 is e to the minus 2t unit step. And this one It's got a third s plus 1, so if we multiply top and bottom by 3, this becomes s plus 3. That's 5 2/3, so that becomes 17 when you multiply by 3. So that's the partial fraction expansion, one line of code. A lot easier than what we were doing. Now, you can do the inverse Laplace transform. You can apply it to the partial fraction expansion, but here I'm showing you, I put y back together, that SymPy doesn't care, okay? You can just give it the rational function like we have in line 10, which has everything combined and multiplied together with the input, the initial conditions, etc. And you just say SymPy.inverse Laplace transform. The calling sequence is you put the rational function of s, and then you need to tell it that you've already defined symbolically s and the new variable time. So we've got two symbolic variables, s, the Laplace transform variable, and time. And there it is. Are you excited? Satisfied? No yawning over there, okay? I'm gonna, yeah, no yawning over there. That's what I'm doing when I look at these things too, okay? So I'm just teasing you. It's not exciting stuff, but it's a very straightforward way to get the time domain solution of a linear differential equation with inputs, okay? It's, and in code, computing y of s and then computing the inverse Laplace transform is quite easy. Questions? Everybody think they can do that? You're going to have to use those commands on the practice final exam, okay? So you're getting very close to the end of the practice final exam. So you may want to know the partial fraction expansion command and the inverse Laplace transform command. You can use them in symbolics instead of SymPy, but SymPy is just a little bit cleaner, so recommended. Okay, so I'm going to move on to qualitative analysis and go back to writing down and just talking us through it, and then we'll come back here. So, okay, where's my Becherel? Okay, so let's move on to something let's do one more partial or fraction expansion by hand, and then we'll do the qualitative analysis. Okay, so let's just practice one more. One more. And then we'll do this qualitative analysis. So let's suppose we've got 2s plus 13 over s plus 2 times s plus 3. So what's the first step? Somebody tell me the first step. We want to write it as a sum of first order terms. Okay, which method do you want to use? You want to do the put over a common denominator, solve simultaneous equations, or do you want to use limits? Limits, thank you. The other one is just kind of brain dead. The limit method is, you know, it's easy enough. So K1 will be 2s plus 13 times s plus 2 over s plus 2 times s plus 3. We cancel those, and then we evaluate at s equals minus 2. And I've calculated that, it's 9, okay? And then, come on. You are not allowed to freeze up. You are freezing up. Okay, you guys get a break while I get this back. Okay. You are not allowed to freeze up. Come on. Save all, please. I don't want to rewrite it again. Yeah. I'm the eternal optimist. It's going to work this time. Just like every time you get a blue screen, if you've got a Windows thing, you go, look, if I just reboot, it'll go away, right? It often does. Yeah. Okay. And then K2 is the same process. It's 2s plus 13, and then we multiply by the root. We have the same denominator. Those guys cancel. This time we evaluate at the root minus 3, and the algebra gives us minus 7. Okay, so if we were thinking of this as y of s, it is now 9 over s plus 2 minus 7 over s plus 3. Then y of t, term by term, 9e to the minus 2t unit step of t. And yes, it is sick to have all of these things memorized, okay? But when you play with them enough, you memorize them for short term anyway. And that's how you get the inverse Laplace transform, in theory. Okay, let's do some engineering practice now. So we're solving differential equations, right, guys? If we want the time domain function, use the ODE tools in Julia. Just stick it in, run it, generate all the plots that you want, and you can see exactly what the thing is doing, okay? So if you need a plot of the solution, why go through 27 steps where you've probably made a sign error or 2 or a half or something, turn that into a Julia function, generate time, and then plot, okay? That's a lot of work. Just put the differential equation in the solver and just solve it. So that's what we do. So if we need the time domain function, using a numerical solver, okay? Just like we would for a nonlinear. We don't care if it's linear. You can solve a linear differential equation with a numerical solver that works for all the nonlinear differential equations too, okay? So we just do that. If we need the time domain thing, we want the plot, we just solve it. Okay. Now, what we usually want when we see the differential equation is we want to understand what it's doing. And if I give you a list of 7 functions that is its solution, you're going to look at that and go, wow, that's complicated, okay? I want to show you how to break it down into something that the human mind can wrap itself around, okay? So we usually prefer qualitative insight over complicated expressions. And it's not because we're lazy as engineers. You know, we're being paid good bucks. If somebody really wants that time domain function, we'll get it for them. We know how to do it. But it's typically not what we want. So I'm going to give you a fairly complicated one. Y triple dot minus y double dot plus 2y sine of t unit step of t. The only thing I'm going to cut you some slack on is I'm going to take all the initial conditions equal to 0. Okay, all the initial conditions are 0. Now, I'm going to show you how you can see exactly what this thing is doing with very little work, just getting the roots. Okay? So this corresponds to s cubed minus s squared plus 2 times y of s equals, and then sine of t is 1 over s squared plus 1. And I'm going to note that that factors as s plus I times s minus I. This thing, I built it so that I would know what the roots are, okay? It's s plus 1 times s minus 1 minus I times s minus 1 plus I. Okay, so this is just kind of easy Laplace stuff so far, and then roots of polynomials. You gotta hand it to me that nothing here so far is complicated. We just factored a polynomial using software tools. And so this y of s turns out to be s squared plus 1, and then s cubed minus s squared. There's no s term plus 2. And if we were going, we're not, okay, we would write this as a partial fraction expansion. Okay, if you want to call those K1, K2, K3, K4, I don't care. I just put in K2 was K1 complex conjugate because this is there, but it doesn't really matter. I'm just kind of reminding us that when the roots are in complex conjugate things. But mostly I don't care what those coefficients are. Why is that? Look at your Laplace transform table. What do these terms correspond to in the time domain? Remember, if it's a plus here, it's a minus there. If it's a minus here, it's a plus there. So this is e to the minus it unit step of t. This is e to the plus it unit step of t. It's the complex conjugate of the previous one. So what do those terms do? What do they do? You know, when I calculate K1 and K1 star and I add them all up, all of the complex stuff drops out. But what does Euler's formula tell us about e to the it? What does it look like? These are all oscillations. Remember, e to the it equals cosine of t plus I sine of t. Okay, I didn't have to write out the partial fraction expansion, but I just thought it would help you focus on why I'm looking at those terms. And I'm missing one term in my partial fraction expansion. Well, that's too bad. Let me add that in. I just realized there's one more term. K4 over S plus 1. Okay, so I'll just take them in the order that they are. So then the 1 over S minus 1 minus I, and the 1 over S minus 1 plus I. What do those terms correspond to in the time domain? So this is S minus something. So it's going to be e to that plus something. So it's e to the 1 plus I t unit step of t. E to the 1 minus it unit step of t. What does this do? Remember, that's e to the t times e to the it. So what does that term do? Tate, no one in the room has a clue, so if you've got one, let us know. Solar, you got it? Okay. Come on, make a guess. So what is the e to the it term doing? Oscillating. What is the e to the t term doing? Exploding. These are exploding oscillations. Okay, that's bad. I don't have to calculate the time domain solution to see it. I just look at the roots. I've got a root with a positive real part. That gives me e to the t. Not good, okay? And then I've got, in addition, an imaginary term, so it's exploding and oscillating. So that robot arm isn't going like this and just hitting the wall and staying there. It's going like this before it hits you, and then it bounces off the wall 10 times and really hits you, okay? That's really bad. So these are exploding oscillations. I know all of that as soon as I calculate the Laplace transform of this term, and then if I introduced oscillation, so I wasn't surprised that there's oscillations in the system. My input is an oscillation, okay? So I'm not surprised. All these other terms, these other 3 roots, so there's 2 roots from the input, here's 3 roots from the system. 2 of them are exploding oscillations. And then the last one is 1 over s plus 1. In the time domain, that's e to the minus t unit step of t. And that's a decaying exponentially fast. Okay, so the point is, Laplace gave us a polynomial coming from the left-hand side of the differential equation. If we had initial conditions, there would be other terms over here, but they're still divided by this polynomial. So we get more terms we get the same terms in the partial fraction expansion. But I don't care what those values are unless they happen to be 0. I got lucky on 0 on the exploding oscillation. You can check that they're not, okay, really quickly. So what do I see? When I have a polynomial here, if I'm looking for a system that is stable, in other words, I've got an inverted pendulum, or your Segway, or the ball bot in Rob 311, you perturb it. Do you want it to start oscillating with exponentially growing oscillations? Probably not, okay? You want it to be decaying oscillation. So you want all of these roots of this polynomial to have negative real parts. If the roots, okay? So the roots, you want minus signs here on the exponentials. You want minus signs if there's an exponential. And I'll show you a video a little bit later maybe sometime next week, of a rocket going up and the PD controller is mistuned. Now, fortunately, the nozzle on the rocket can only go plus minus 25 degrees. It can't oscillate to infinity, so it just hits one end and it bounces and hits the other, okay? And it's oscillating fast enough that the base of the rocket stays fairly constant and it goes straight up. Pure luck, okay? Okay? If that oscillation been a little bit slower, then the rocket is doing this and it breaks in two. And if it had been faster, it would have just broken the nozzle off the rocket. So they got lucky. They had a PD controller with positive poles with a positive roots with a positive real part. It's got exploding oscillations, but because of the nozzle being limited, what it can do, the rocket doesn't blow up like SpaceX's do a lot. Okay, so the qualitative message if the real parts of these roots is negative, we have decaying exponentials, and it's with or without oscillations depending upon if there is a non-zero there's a non-zero imaginary part. The real part of a root is positive, we have exploding exponentials. And we don't even need to look at the time domain terms often, because we're going to go back in and fix it so that it has decaying exponentials or at most oscillations, okay? With or without oscillations. Depending on if the imaginary part is zero. And then if the real part of the root is equal to zero, it's either a constant if the imaginary part is zero or oscillations. That's amazing, okay? Just from the roots, okay? Just from the roots. Now, where else did we see something like this in our tour of differential equations? Anybody remember where we may have seen rates of growth popping up? Okay, everybody's feeling timid today. Okay, the real part of eigenvalues, yep. Excuse me? Yeah, the eigenvalues of A. So if the real part is positive, boom. Real part is negative, comes down. If there's an imaginary part, homework 8 lets you understand how the oscillations, yeah. So it's similar. There's a lot of parallels here. And in fact, under conditions that we know how to quantify carefully, the eigenvalues and the roots will be the same. Okay, so let me show this in code. So it's the same ODE. So it's the s squared plus 1, that's the sinusoidal input, and then the s cubed minus s squared plus 2, that's from the body of the differential equation itself. we can do the partial fraction expansion, okay? We can compute the inverse Laplace transform. And yeah, so now we know the exact coefficients, okay? Theta of t, that's the unit step. E to the t, we know where that comes from. The e to the minus t, we know where that comes from. The cosine, we know where that comes from. The pure oscillations with no exponential term, we know where that comes from. Okay, that comes from the s squared plus 1. This comes from the s plus 1. And this s squared minus 2s plus 2 is what gives rise to this term. But we already knew as soon as we looked at the roots that we had these growing oscillations present, and that was not good. And this is only third order. If we make it fourth or fifth order, I don't know, it'll probably crash. Probably crash it, but let's see if SymPy can handle it. My kernel had turned off. That's what's going to save you. You don't have to compute it. SymPy not defined. It's defined now. Now you got to do something with it. Okay, so my point is getting long expressions like this is not really helping you. As soon as if I gave you the roots of that polynomial, then everything would be done. So we don't, in real life, compute the inverse Laplace transform very often. We try to look at the Laplace transform itself, analyze it, and then modify its behavior to make it do what we want it to do. That's what real engineers do. Now, in your engineering courses, they'll make you compute a few inverse Laplace transforms and then ask the professor how often they do that in their own research. Okay, just ask them. Is that important in your own research? Any of your colleagues' research? Any of the consulting jobs that you've done? Okay, just ask them, and they'll tell you no. How we doing? Okay. Time domain function, Laplace transform, frequency domain. No, for you, time domain, Laplace transform, frequency domain. We go back and forth in a straightforward way. It's algebraically painful by hand. In code, not so much. So we can do those. But the Laplace transform allows us to break the differential equation into a part where we can get the roots. Those are the things that show up in the partial fraction expansion, and if the roots have negative real parts, everything is decaying. We've got stability. That's really good. Now, can we apply Laplace transforms to x dot equals ax, state variable models? It's the models that's plural. Oh, let's do one. X dot equals minus 5x1 plus x2 plus 7u. x1, 0 minus equals 2. x dot 2 equals minus 6x1 plus u. I'm going to make it triangular, easy on us. I'm going to define an output. Could be like lean angle or velocity or something. And our input will be our usual tame decaying exponential, just because it gives us 1 over s plus 1, something easy to play with. Okay, so if you wanted to apply Laplace to this, could you? And the answer is, yeah, what the heck, why not? What's the Laplace transform of x1 dot? That's s1, x1 of s minus x1 of 0 minus, okay? Do it term by term. Minus 5 x1 of s plus Laplace transform of x2, x2 of s plus 7 u of s. I just do it term by term. Okay? And there aren't any second derivatives, so it's kind of easier in some sense, right? S x2 of s minus x2 of 0 minus equals minus 6 x1 of s plus u of s. And then the output y of s equals x1 of s. So, we have an input. It's given to us. We have initial conditions. We just plug them in. So we just plug in x1 of 0 minus equals, what was it, 2? Yeah. x2 of 0 minus equals 13. U of s equals 1 over s plus 1. And solve for y of s. Nothing easier. Okay? We can solve for x1 and x2. We'll have two equations and two unknowns in the top. U is no longer an unknown. It's 1 over s plus 1. And then we get x1 and we plug it into y. So, just straightforward algebra. Straightforward algebra, except, I don't know if you guys have a fond memory or not of the first lecture in Rob 101, where we write down two equations and two unknowns, and we go through and see what can happen there, and then we put three equations and three unknowns, and we try to do all of the elimination and back substitution and solving, and it's just, we very quickly said that's not going to scale, and we went to vector representations of what's going on. So so Monday, the vector matrix view. Of x dot equals ax plus bu, y equals c times x. Much nicer than what I just did, okay? It'll be much, much nicer. So, that's enough for today. Yeah, you can do it, so you can just see it, just apply Laplace transforms. And you just got to set up and solve simultaneous equations. So, but we'll do it directly next time. It'll be a lot easier, So thank you.